The afternoon portion of our seminar begins with Michael Griffin, a principal at Creative Construction Solutions. Michael has more than 30 years' experience in practicing earthquake engineering. He is one of the primary FEMA trainers in teaching the earthquake evaluation and mitigation of damage. Michael, as I call you up to present, we know we live in an area that does experience earthquakes. Most of them are never felt, though. Did a little research. According to the Weston Observatory, which tracks earthquake activity, the last shake in New England with a magnitude of 2.7 or greater occurred on September 26, 2010 in our neighbors to the north, New Hampshire, up in the Lakes region. No damage was done, thankfully, but a reminder that New England is not immune to earthquakes. So, Michael, come on up. Thanks for joining us. We look forward to your presentation.
Thank you, Peter. I'm going to apologize right up front here. I feel like a fish out of water. I'm a structural engineer. I'm not in the medical profession. And where did they, engineers are typically boring, right? Equations, that's all you're going to see here, right? And what have you just had? Lunch. So my job, I feel, is to try and keep you awake more than anything else here. I'm going to take a little bit of a departure as well. This morning we've heard about preparedness, which is vitally important. I fully believe in that as well. But coming from a structural engineering background, I also look at preparedness as what can I do to mitigate some of the consequences associated with these events. And so hopefully, at least on the structural side, impacts to your organization, I'm going to hopefully leave you with some guidelines here that will help you mitigate some of those consequences. So after the event, your facilities will be in a much better state to actually provide that critical care of which that is your charter. So with that, Peter mentioned I'm a structural engineer, earthquake engineering. I've practiced that my entire career. I started my practice in California, so there's the connection. I now reside in St. Louis, and I continue to practice that. I also do a lot of high wind, hurricane, tornado engineering as well. Extreme events is what I like to call them. So I've got a very good background in how buildings perform, how the critical equipment and systems, the infrastructure performs in building structures, to hopefully give you some guidance into how you might be able to mitigate some of these consequences associated with these events. So today we'll talk a little bit about natural hazards. We haven't heard much about earthquakes, and I'm going to talk a little bit about earthquakes here. We're also going to talk about risk management. How can you manage these risks in a much more proactive, much more cost-effective method than just waiting for it to happen and try to plan that way. There are things that you can do very cost-effectively. And then I'm going to talk about mitigation. What are some of the simple things you can do, straightforward things from today going forward that really cost you very little in premium to actually implement? It's just understanding the design process, understanding your design professionals' capabilities or lack thereof, and then ensuring that they get the people, the necessary people on your design teams to actually implement some of those improvements into your facility. So hopefully I'm going to leave you with some of those tools at the end of the day here. Natural hazards. Your environment is one that has many, 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 many components in it. It's not just the facility, it's everything inside the facility. Your critical care, your ORs, your intensive care units. That's a lot of equipment and systems that go into supporting your function as a critical care facility that you have to be worried about. And in fact, we'll talk about this later, the building code requires hospitals to have a higher level of design attention than a normal facility. The question is, are you really getting that from your design professionals? That's a serious question to ask. If we look at some of the risk from natural hazards, hurricane, you guys aren't immune, right? You've had several of them that have come through here already, recently. They're not as strong when they get up here to the northeast. However, what comes along with hurricanes usually? Water, flooding. So you've got that additional consequence to deal with as well for hurricanes. Flood risk, you can have just floods from heavy rain, but hurricanes dump a lot. The picture on the left is the hospital in Charlotte-Amalie in the Virgin Islands after Hurricane Opal in '95. That's their records area, located right next to the side of the building. They breached the pressure boundary on the exterior of the building. All their records were damaged from the hurricane. We'll see an example here a little bit later on an earthquake in Chile where the medical records were damaged. They were all over the place. Their casework actually fell over. There was a team there doing an investigation after the earthquake. There was someone sitting there literally putting all of the medical records back in the appropriate folder 3 weeks after the earthquake. We heard about digital records are great, except when you don't have power to access them. That's true. The example on the right is from Hurricane Katrina in 2005. They had some breach in the facility. However, they had 6 inches of water in the lower levels. So is your OR down there? That's tough. Tornado risk. We just heard from Joplin. I'm a little close to Joplin as well. I'm part of the Missouri Save Coalition, which the Missouri Save Coalition is volunteers that we've trained to actually do damage assessments after a major disaster. Because recognizing, just like MRC, if I got that right, the Medical Reserve Corps, just like that, the buildings have to be inspected for safe occupancy after a major event. And you can imagine the local building officials don't have that capability. So Missouri has created their SAVE coalition that actually is made up of volunteers to actually deploy into these areas and assess damage. We red, green, or yellow tag them for occupancy. And we are, just like mentioned earlier at Joplin, we're like 72 hours beyond because it's all search and rescue first. Then we start looking at cleanup and recovery, and that's when we go into there. So similar program, we dispatched 69 volunteers, and over 3 days we looked at 7,700 buildings for occupancy. And this was not the main swath where you saw the pictures. There's nothing there. Why bother? This was the outer fringes to where our teams were actually doing an investigation. So tornado risk, again, you're moderate up in this area. Joplin. The interesting thing about tornadoes, remember what he said about the tornado. If it had been displaced a little bit more to the south, it would have taken both hospitals out. Now this is a low earthquake seismicity area, but if you're in a higher earthquake zone, they would have both been affected, as well as a very much larger geographical area from an earthquake. And that's the problem with earthquakes. They affect a much larger area. Tornado-wise, in terms of geographical impact, is nothing compared to a major earthquake. There's St. John's. They had extensive breach of their pressure boundary, the exterior cladding for there, which totally messed up the interior. Everything. Function, they couldn't function. Talked about tornado sirens. We have warning for hurricanes. We have warning for tornadoes. Do you have a warning for earthquakes? None. They're happening right now. So you have to decide what you're going to do in an instant. Patience and care. That is the scary thing about earthquakes. This is their central energy plant. This is their infrastructure. Heating and cooling, power. Doesn't look too good. This is all preventable. Even for winds as high as this is preventable. Earthquakes. I like the nuclear explosion this morning because I was trying to look for something to grab your attention, because earthquakes are like that. You don't know if they're happening. So instead of surprising you, I make you laugh. That's the problem with earthquakes. You don't know when they are going to occur. Now notice up here in Maine, if I can, well, let me see. I'll do this and then I'll go back. Oops. There. Okay. So we all don't get sick. Notice up in Maine, you've got to the north, or in Massachusetts here, up to the north, you've got moderate level of seismicity. And you guys are kind of in a low. It's not zero. White is zero. You guys are actually in a green zone there. So there is earthquake activity. There is seismicity potential. Your boundaries are up to the north as to where we see a lot of the seismicity, the higher level of seismicity, and then to your south. So you're kind of sandwiched. At least that's what the geologists and seismologists tell us today. They're still learning. They've been trying to predict earthquakes for I don't know how many years now, particularly in California where they're more frequent, and they've missed the mark. So take it with a grain of salt, if you ask me. This map simulates very well the actual seismic design provisions in the code, the building code. If you are in white, you don't have to do any seismic design. If you are in any of the colored areas, from the lighter to the darker, it's a higher level of seismic design attention. That's required by code. Your design professionals hopefully know that. Out here, for a normal building structure, wind will typically control the design. Earthquake will not. I said a typical building, office building. For a hospital, because you're designing to a higher level of performance, for earthquakes and wind, seismic will control. So you need engineers on your team that actually understand seismic and are actually going through and doing the seismic calculations. Just to show you, we have two issues to worry about for building structures. There's the structure itself, and then there's everything in it, which is the non-structural components. And I'm going to talk a lot about that, because that is what your risk is here in this low environment for seismicity, is the non-structural components. That affects your function. That's everything inside. I'll show what the building structure is. If you have a normal building and you have a life safety system inside of it, it's supposed to garner a higher level of seismic design attention. Emergency generator, right? Doesn't matter if it's an emergency generator, it's a life safety system, you're supposed to design it for seismic loading. You're going to think I'm weird, but I am an engineer. I walked around the hotel. They have a nice big emergency generator sitting right outside here. Guess how well it's anchored? It's not. It's a life safety component. And I can tell you, even a small level of shaking will move that generator and make it walk. And what comes up from the bottom of it? All the conduit that feeds into the building structure. So now I have a massive piece of equipment that's literally walking, and it's going to sever that piece of a conduit, and my generator is toast. It's supposed to have required, or had allowed, the seismic design for it. I'll go through a lot of those examples, and this is understanding this type in the design process will help you with your projects as well. Okay, we don't want to see that shake anymore. Just to show you what small earthquakes can do, this is the mineral earthquake, happened down in Virginia. Did anybody feel it up here? Yeah. Outside of California, seismic waves travel very efficiently in the soils that we have. So even large or moderate earthquakes at a distance can travel and affect and actually re-amplify, if your soils are poor underneath your building, to much higher levels. Soil is one of the big things we worry about in terms of structural design. Some minor building damage, most of it was non-structural. $200 to $300 million in damage. That was a small event, 5.8. Non-structural was the most of it. Think of your facility. Ceiling damage is coming down. Do you know what's above a ceiling plenum? Dust, dirt. It's all the utilities, but it's not clean. So now you've opened up that environment to critical care, which is not good. What do we do now? So preparedness is important. All this damage that you've seen here is very, very preventable. And it's hardly a premium to actually prevent this type of damage. Have you seen this? This is actually the Louisa School. And they actually got the corridor here on their security camera filmed. Ceiling tile won't kill you. A light, 2x4 light, might. This is all preventable. And actually, you don't even need to hire me to tell you how to fix it, because this is all prescriptive criteria in a standard. It says, Mr. Contractor, build it just like this. And the provisions work extremely well. The problem is enforcement. Then you can see they're all running out. I got a good exercise for earthquakes. We're having an earthquake right now. What are you going to do? Go with me. I'm diving under that table. Drop, cover, and hold on. That should be automatic. Drop, cover, and hold on. And the reason is, right here, we've got a lot of non-structural components in the building structures that are going to fall down in even minor earthquakes. That's why you want to get under a table. So that should be part of your earthquake preparedness for your staff in your facility. Everybody's looking at the lights. Yeah, right at the lights. They're supposed to be safety wired. Supposed to. There's Olive View Hospital. There's a story of Olive View Hospital. This is 1971 San Fernando earthquake. This is a brand new hospital. After the earthquake, it actually shortened a little bit. We actually pancaked the first floor. That is the stair tower on the right that is actually rolled over, lying on its side. This set off a fairly large amount of concern in California regarding seismic safety of hospitals. After the Northridge earthquake in '94, the state really got involved. But it's not only buildings, it's the interior too. Non-ambulatory patients aren't even able to get out of the way. Earthquakes follow all of you. This is after the 1994 Northridge earthquake in Southern California. This is their new facility they built after they basically demoed the old one in '71. This has state-of-the-art structural lateral force resisting system, which is the ability to resist lateral forces to the side. State-of-the-art. The building structure did fantastic. No damage at all. They still had to evacuate patients from the facility because of what? Non-structural damage. That's water from a leaking sprinkler pipe that was damaged in the earthquake. Just to show you how difficult it is, and I don't know why, I've been not able to figure this out. I have reasons. This is, notice these little, this is a motor control center, which is power feeds through into your facility and distributes it. Notice these little angle clips on the bottom here? Those are non-standard. That's a retrofit. So here you have a brand new state-of-the-art facility. They forgot about the equipment, and they had to come back and put in this retrofitted system here. The manufacturer provides anchor bolt holes to put an anchor bolt in, yet they didn't do it. So they dropped the equipment, and they finally came along and said, we forgot something. We need to anchor this equipment. So it's not just the building structure, it's the non-structural components. This is Chile. This ground motion level at this hospital was slightly above the ground motion design level for here. This was in Santiago, about 200 miles away from the main event, so the ground motion was not that high. So now, can you imagine your facility operating after an earthquake with this damage? That's non-structural. The building was fine here. So if we look at, Mike, your death and destruction, shoot, what's this really mean to me? Well, there's a study that was done that kind of illustrate this in terms of how much damage could you really expect. And they looked at hospitals in California because they had all this data and they had frequent earthquakes out there. By the way, California is unique in that they do have these frequent earthquakes. So what does that do? It weeds out all this old building stock. Then they build back new. Problem is, outside of there, we don't have that luxury, and we've got a lot of old building stock for earthquakes. They looked at these 218 hospitals, and they looked at 1973 as sort of a benchmark year in terms of design improvements. Why 73? All of you hospital 1971. Design provisions took 2 years to get adopted into the codes, and now they're building better. So they felt any hospital of these 218 before 1973 was representative of the hospital building stock outside of California, is what their contention was. And then after 73, where design was much better, it should be reflective of newer design provisions. See how things perform. They looked at both the building structure and non-structural components. So they did this where they binned it by ground motion level, shaking, in different categories. So it's not all smeared together as one. They looked at very thin slices of the data in terms of how hard the hospitals were shaken. And I actually pulled the data for the ground motion level used here in the building code today for this area. And what you'll see is the pre-73 is here, and notice the level of damage for the building structure. 71% of the building structure is no damage. And then we had 19% minor damage, and then 6 and 4, where you had pretty significant damage that's going to affect operations. If you had new design provisions, your building structure is going to do much, much better. Non-structural, 34%, 46 had minor damage, 15 and 6. So you had roughly, what, 60+%? Some level of non-structural damage to your buildings, or non-structural components, only 34% without. Now, if you look at the performance, if you do incorporate some higher level of design provisions, we get out of this category, but you still have a fairly high percentage of minor damage. That's drywall cracks, that's ceiling tiles down, so we're still opening the ceiling up, but it's still fairly high. And this is from California hospitals. The structural engineering community today is doing a very good job on building structures. We know how they behave in earthquakes, and we're able to design for those forces very, very well. What's not being done now is on the non-structural component side. That is not a structural engineer's responsibility. That is the architect, that is the mechanical engineer, that's the electrical engineer. But they don't know seismic. So more times than not, 95% of the time, those things don't get done. I'm a rarity in that I know about non-structural components. So, but this just illustrates that it's not death and gloom. Building structures do fine. They don't fall down. They really don't, particularly at the shaking level here. But you still are going to have some fairly significant problems at lower ground shaking levels for the non-structural components, which affects your operations. So if we look at risk management, I know you all have risk management departments, right? How many of you address natural hazards within that? Okay. How many of you do you absolutely know what the risk is from those natural hazards to your facility? Or are you just planning in the event of one? You're likely saying, if we have a tornado, we're going to do this, this, and this, right? But you have no idea how your facility is actually going to fare. Correct? That's the first thing when you look at any level of risk reduction is, what is the risk to my facility from high winds, from flood, from earthquakes? Because then once you know the risk, understand the risk, now you can begin to make appropriate decisions with regarding how best to mitigate that risk and or plan for the consequences of that risk. That's key, the risk assessment. Here's the only equation I'm going to show you. I'm a big proponent of mitigation because you can either pay me before the natural hazard happens and affects your facility, or you can pay a lot more after in trying to fix it up, recover from it. Just depends where you choose to spend your resources. So I'm a big proponent of mitigation because, in my opinion, it's a lot cheaper to pay for that mitigation up front than it is to recover and pay for the repairs afterwards. So this is the equation for that. We have the risk is a function of our hazard and our vulnerability. The hazard is what it is. You've chosen to live where you live, along with the hazards that affect that region. So hurricanes here, we saw moderate risk. You've got flooding potential, you've got tornado potential, and you have a minor earthquake potential. You've chosen that. We can't do anything about that. However, we can do it on the vulnerability side for both your building structures and your non-structural components in reducing that risk. And that's what mitigation is. Some of the effects of that, it's easy to get our heads around direct property damage, what's damaged, and then what the potential costs are associated with recovery and restoration. But there's a lot of indirect. Loss of facility operations, loss of service to the community in the greatest time of need. I just remember the Joplin speech just before lunch. They're bringing them in truckfuls. That is the expectation for a community, right? You guys are up and running, right? Where's everybody going to go? We're going to go to the hospital. So there is a significant amount of expectation from the community that you guys are prepared. You guys are going to be there. That's a huge burden, if you ask me. So there's loss of service to the community, loss of goodwill because of that expectation, and then you've got patient evacuation and relocation. That affects care for those people, and then potential loss of life to worry about. 3 things you need to worry about: life safety, for one, for your staff and patients, property loss, direct damage, and then also functional loss. Are you going to be able to provide the critical care services? First thing, when we look at the risk management process, is what we want to do is do a risk assessment. There are so many different tools out there available today that you can actually do that, both wind and hurricane. FEMA offers a free program. You got to buy ArcGIS, which is not cheap, to actually utilize for hurricane risk, wind risk, flood risk, and earthquake risk. It'll actually calculate it. And in fact, most of the states today have HAZUS, Hazardous US, that's the program, HAZUS US, to where they've actually modeled in the critical facilities, so police and fire and hospitals. Now, what data they have for your facilities in that, I don't know. But that's something you might want to talk to your state emergency planning group and see if they've actually done a HAZUS run. And they'll have looked at that. That's a first start from some very basic data. So they're going to know, given these various natural hazards, who's going to be up and operating to some level or some degree between them. So they're going to know on a state level where I need to send people. in that regard. So that's the basic, what we call tabletop. After that, there is what we call a rapid visual survey. There's tools available that you can actually do a fairly quick risk assessment to understand what the risk is to your facility, your building structures. And then after that, you're going to look at doing a fully detailed engineering assessment where you're going to hire structural engineers to come in and actually do that assessment for both building and non-structural components. Once you have the risk assessment, you rank and prioritize, then you develop your mitigation plan and begin to capitalize and perform the mitigation. I make the comment, mitigation doesn't happen overnight. It can't. So don't be overwhelmed. I will leave you today with some very straightforward ideas to how you can begin to look at mitigation. And then, does anybody know if a tornado is going to hit their facility tomorrow? No. So why do you have to do mitigation overnight to harden your facility? You don't. But over time, if you just nick at it, when the time and it's more cost effective for you to do it, eventually you're probably going to get hit. You're going to be much, much more prepared than you are now than doing nothing. So that's what I advocate in terms of mitigation, how it should be done. Let's look at these two different terms. There's structural components and there's non-structural components. This is extremely important because when people think my facility has been designed for earthquakes or high winds, it invariably only involves the structural portion of the building. That's just the building structure. This photograph here shows what we mean by the structural aspects of your building. That is it. Literally, everything else falls into the category of non-structural components. And that's a lot of stuff. That's your cladding. That's your interior finishes. That's your partition walls. That's all of your critical medical equipment. That's all classified as non-structural components. There is a huge difference between who and what designs the building structure and non-structural components. Non-structural components is everything else. So when someone says my building's been designed to the latest International Building Code for high winds and seismic design, I can guarantee this is all they're talking about. More than likely, they haven't paid any attention to the non-structural aspects of the building structure. That's critical to understand and critical to know. If we look at structural systems, they're designed by a structural engineer, so be it seismic or high winds, he's designed the structure to resist those forces. He puts that information on the construction drawings and the plans, and they're built. Whereas non-structural systems, the structural engineer is not even involved. It's the mechanical engineer, it's the architect, it's the electrical engineer that knows nothing about seismic. And in fact, they don't, so what they do is they write a performance specification that then goes out to the contractor to actually implement the design provisions for those components. So here we've advocated or pushed all of the critical design, natural hazard design provisions onto a contractor to implement, the least qualified. And you better hope you have a good building official so he is able to look and catch and enforce the provisions, which doesn't happen. That's why we see so much damage in non-structural components. That's one of the main reasons, is right there. So a tip, if you're involved in the design process for anything that you have in your facility, be it a renovation, patient care improvements, a new building addition, ask these pointed questions of your design professionals. Who is actually doing the seismic design, the high wind design for these components on my design team? Oh, we're taking care of it. No, no, no. Who's doing it? Do you have somebody that has expertise in this area that's actually handling it? The structural engineer is designing the building. Who's handling the structural aspects for the non-structural components? Unfortunately, this is what it oftentimes takes in terms of getting that level of performance out of the design community, unfortunately. The reason I mention non-structural components is it affects function in your facility, and where is all the value? If you look at this slide, for a hospital, only 8% is in your building structure. Everything else is non-structural. So if you do some level of risk mitigation, it doesn't take a rocket scientist to figure out, I'm going to address where all my money is. That's in all the non-structural, because that affects you so much. And like I said, structural engineers today are doing a very good job on the building structures. So there's other reasons why we see problems with the non-structural components. There's the code design philosophy. It is a life safety performance code. It literally is. It's a life safety performance. So if you want a higher level of seismic design or wind design attention, you have to go beyond that. Non-structural importance factor is supposed to be assigned to every component to let the design team, everybody understand and know what is the level of performance that we expect out of that component. And I can almost guarantee anybody in this room is involved with any addition or renovation. Has any of your design professionals sat down and said, this MRI here, is this a critical piece of equipment for your hospital that after a major event, tornado, hurricane, earthquake, I absolutely need that functional, so I want a higher level of design attention. Mr. Owner, do you? I can almost guarantee no one there has had that question asked of them. Yet, your design professionals are making these decisions. They are deciding for you which is what is important after a natural hazard event, if they're even doing that. Life safety system, fire protection is a life safety system. Chemicals are life safety systems, supposed to have higher level of seismic design attention. Emergency generators for emergency power are life safety systems. So those elements typically get a higher level of seismic design attention, are supposed to. Not all components are governed by code. We have exclusions. That's what I meant. If it is important to you, you need to reflect that to your design professionals so they account for it. Screen viewers, portable rolling equipment, those aren't covered. Typically owner supplied. So lab equipment, tests, desks, everything on top, that's all non-structural components in terms of performance. And a lot of those can be life safety risks as well. Then we have, for non-structural components, I've alluded to this already, who's responsible for the design. Happens to be a lot of folks to make sure it gets done right. And what you'll notice here, purposely, is on this side where we have engineers, structural, mechanical, plumbing, fire protection. Do you see anybody addressing a higher level of design attention for seismic or high winds in any of these systems as an expert? You don't. They rarely exist. So a good architect will actually hire somebody that has that experience to put on the design team just like he does any other professional for that. So this is where you have an impact. You can actually insist upon that within your design team to go forward. Responsibility. These are from seismic events. Remember the Allevue Hospital and the water leak? There was no fire, but it's a water leak. So who's responsible? Is it the architect who's responsible for the ceiling, or is it the fire protection engineer who's responsible for the sprinkler system? They all have to work together. That's an owner-supplied set of bookcases. Who's responsible? Who's responsible? Is that the structural engineer because he designed a building that was flexible and actually displaced to absorb earthquake energy? Or is it the architect who didn't design enough flexibility into his glazing system attached to the building structure that all the panels broke and popped out? Who's responsible? All your design professionals need to be talking to each other when it comes to natural hazards because they all interact. This is my favorite. We have a very significant lack of construction, inspection, and enforcement. This is not to belittle building officials at all, it's just they have more critical things than looking for improvements that need to be installed for natural hazards. They're just normal operations of the building structure. And so we have issues, particularly for earthquakes, where this example here, this was a hospital building that was 150 feet by 300 feet long. The sprinkler contractor came in and installed the sprinkler system, and he put a head right underneath. This is a steel beam with fireproofing on it. He put a fire sprinkler head right beneath this steel beam. When they lay this pipe out, it's 10 foot on center. Put a head, 10 foot a pipe, put a head, 10 foot a pipe, put a sprinkler head. 150 feet by 300 feet long. Guess what the beam spacing was at? 10 feet. You will not catch this on drawings. You can only catch this by inspection in the field by someone knowledgeable about it. So this was a 7-story hospital building. This was at the top floor. Guaranteed you're going to pop a head with this type of installation, and where's all that water going to go? Down 7 floors. I've been involved in a bank building, 3 stories, nice and flexible building, which is problematic, but it absorbs energy in an earthquake. Sprinkler head popped, it found a conduit, went all the way down to the 1st floor where their data center room was, flooded the data center gone. There was no fire, by the way. Here's another great one. This happens to be right at the intersection of 2 separate building structures that were built. So there's a seismic separation, so each building can do its own thing during an earthquake. Well, the fire protection contractor did his job in that he designed, this is an 8-inch diameter pipe. It's a lot of water. He designed a flexible pipe system that went across this joint that would accommodate the differential displacement of the buildings. Well, the drywaller came along and said, I'll just drywall around it. So now you have a main water feed main going from one building to the next right across this seismic joint that's been locked in. 8-inch pipe and a lot of water. This was an installation where at least the contractor put an anchor bolt in there, but it looked funny to me and I literally pulled it out by hand. You would be surprised. I can show you picture after picture after picture of this. Construction inspection. Do not let your design professionals skimp on it, and don't do it. You have to. This is the last opportunity to make sure that what you're buying has been installed properly to get you the performance that you are expecting out of your design professionals is right here. All the drawing and the paperwork can go out the window. It's right here. This is where the rubber meets the road. Just to show you how non-structural components can behave, this happens to be a video, very informative. This is one of the largest shake tables in the world in Japan. What you'll see here is 6 panels. There's 6 rooms that they've sort of mocked up in terms of an office, a bedroom, a retail display, and that sort of thing. And we'll see overall shaking here, and then we're going to look at a close-up of what happens inside. Now, what this is modeling is non-structural components, but even on a simpler side in that it's contents. This is what's inside the building. It's not drywall finishes and lights and stuff. It's just contents. And you can see what an earthquake, even low level of shaking, can actually do to this. Joe, you want to turn it down just a little bit? There we go. Now look at the overall movement of the building. Does that look severe? No, it doesn't. It's long period motion, what we call long period motion, and it basically is Doesn't look very dramatic, does it? Come on, Mike, this is terrible. I can't even see anything here. This is barely moving. Well, wait. Now we're going to see individual cameras inside each of these different panes. This must be with the video equipment here, because normally this doesn't run this slow. Typical office. Those are your medical record cabinets, bookcases. Do you have a killer copier? Remember the overall picture. Did it look that violent? Problem is, non-structural content systems are affected by even small amounts of shaking. So what if this had been an egress corridor right through here? Pretty tough to get out. This is where you want to drop cover and hold on. Now, there are some mitigation techniques used here. Notice the laptops. Notice this tall, skinny CPU on the table here. Lock those wheels. Yeah, but notice the CPU stays on. You can actually get this double-sided tape. That actually works very well. All right. Watch the cabinets. And this mannequin here, our specimen, actually does his job. Drop, cover, hold it. Notice the bookcase. That's a simple clip to the wall. You've just mitigated that damage. This is a retail space. I always kid, this is me waiting for my wife to finish shopping. That's a trip to the emergency room there. So contents, and this is where you and particularly your facility staff can do a lot about mitigating these risks. Everybody already guessing what happens here. I don't have to show it. Notice if the earthquake stopped, it would be over. Yeah, they did a good job. Like I say, this is some of the early research being done on non-structural components. There really hasn't been done. Notice the refrigerator. You've got a lot of those, right? Probably with some very important lab work in them. Not to mention the women there. Again, very straightforward, very simple clips and anchors mitigate this. Now you don't have to worry about cleanup, potential damage to the equipment and systems. So they're actually doing some very good work. Okay, moving on. Mitigation, I want to get through this. How am I doing on time? All right. Okay, what are the benefits of mitigation? Well, life safety risks are reduced, both for staff and patients and visitors in your facility. Naturally, your costs for recovery and cleanup are reduced. I remember the million pounds of debris that from Joplin they have to get rid of. You won't contribute to that. Functionality. You are going to be in a much better position for your facility to be functional after a major event than if you didn't do any level of mitigation. So you pay before, you pay after. That's really how you have to look at it. And in fact, FEMA has actually attached a dollar amount to it, particularly for non-structural components. They have projected that for every dollar spent on mitigation, you are preventing $4 in worth of damage, repair and recovery costs. That's significant. That's a benefit cost ratio of 4. Anything greater than 1 says it makes sense to actually implement or do that. And in fact, I don't have time, as hospitals, critical care facilities for the community, the federal government, through FEMA, actually awards money, grants, for mitigation that you really need to look at, even if you are a private hospital, because of the importance of your facilities. That's something to look into if you're embarking on a major mitigation program, is FEMA grants. Non-structurally, your maintenance guys can actually implement a lot of this stuff, which is the beauty behind it. I'll show some examples. And we already saw the chart in terms of this is your non-structural components, this is your largest financial outlay for your facility. This is where you need to really focus. And did I mention it helps with life safety? Okay, as far as mitigation go, you can do nothing or ignore the risk. You can accept it. It might be to your surprise that you're pretty well prepared. Your design professionals are doing a great job. I'd love to hear that. You can modify your business and response plans as a result of your risk assessment, because now you understand how bad or not bad it is. So now you can adjust your response plans to it. And that makes a lot of sense, but only after you understand the risk to your facility. You can adjust your business operations. If you've hospitals, you guys have multiple buildings and you're using them for different things. So if you've done a risk assessment and you have a building over here that is a high occupancy, critical function in a very lousy building, but you have lower occupancy in a much better building over here with less critical functions, why not plan at some point to swap the functions in these buildings? Put lower occupancy into your bad buildings and take your newer buildings and put in your more critical functions. You're not going to know that until you do a risk assessment. You've done no structural improvements, none at all. All you've done is, hey, I have a poor building here and I have a much better one here. I'm going to put my good stuff in there. That's mitigation, folks. You don't need to hire me to tell you to do that once you do your risk assessment. Perform facility strengthening. That's always a challenge and costly when you do that. Non-structural mitigation through component strengthening. You can do an incremental seismic mitigation program. FEMA 396 is a very good tool for that, particularly for earthquake mitigation. Likely your plans, any mitigation plan, are going to be a combination of the above. There's not one size that fits all. Your challenges to the hospitals, you guys are at 24/7, no swing space. It's difficult to get in there and actually do the work. The thing is, you're going to want to do this when it's on your time and your dollar, rather than have a major event and then all of a sudden there's going to be public outcry and hysteria over why is there so much damage after this major event. And then they're going to say, all hospitals have to be upgraded, and you have 5 years to do it. Now try to function and do that. And you think I'm crazy. You guys know what's happening in California, do you not? That's exactly what California has done through OSHPD. They have to actually seismically strengthen all their buildings. Unfunded mandate. So don't let that happen. I'm not sure what's going to come out of high wind safety improvements for hospitals after Joplin. I haven't heard any discussion yet on that, but it wouldn't surprise me to see some level of higher level of performance for that. So if you're mitigating as you go, making sure things are built right and correctly, if and when that happens, you're going to be in a much better prepared position to actually deal with that. Okay, non-structural components, very easy. Good housekeeping goes a long way in terms of, particularly for earthquake performance. You have corridors that look like this, right next to egress routes with stuff on top. Good housekeeping. Very simple for a lot of these life safety things, nuisance things, you can actually restrain. There's a lot of proprietary details that are available out there that you can actually do this. If you do any level of mitigation, construction inspection is important. This is not a proper anchor, I will tell you now. What happened here, the engineer designed the anchor, And he said, oh, this piece of equipment, all you need is a 3/8 inch anchor bolt. Mr. Contractor, go ahead and throw it in. That's okay. Well, the problem is the manufacturer provided a hole in the base that was big enough for a 5/8 inch anchor bolt. And so now you throw a little 3/8 in there, and now this thing starts to overturn and rock. You basically suck the nut and the washer through, and now you have no restraint. The engineer was smart. He saved you 50 cents on that anchor bolt, times 4. You feel good about that, don't you? That happens more than you think. Do it right the first time. This is a generator at a mental health facility that I surveyed. They knew they had to do something because the generator was what we call, it's on vibration isolators, which are non-seismic, so they would have failed easily. I'm not a betting man, but these things fail all the time. So they chained it. Seismic chains? No. Properly anchored. Here's a retrofit for an uninterruptible power supply. This is your UPS batteries for your computer systems. Notice how it was properly installed. That's the retrofit. How much do you think that cost? For that entire cabinet, 4 of these in each corner, less than $300 installed. You mitigated the risk. Why don't you do that? It blows my mind. It's not done. How do you think they restrained that? Straightforward. They braced it, put some false casework to the ceiling, and braced it above. Very straightforward. Refrigerators. Restraints top and bottom. These are ugly. They actually make some better ones today where you can't even see them, where they attach to the wall and then to the top. And then restraints here. You can't just do the top because if you have anything here at the bottom, the base will just walk out on you and then just collapse backwards. I've seen it quite a few times. Here is some more content restraints. Very, very simple, very, very straightforward. Be smart about it. This example on the right-hand side was a medical manufacturing company that I did a survey for. I was talking to the facilities manager. He had these racks that were all nice and bolted together, nice, wide, stable configuration, and he had all these parts bins with bolts and nuts for spinal surgeries and all that stuff. I'm amazed what you guys throw in bodies. So these are all different length, size, bolts, and everything. 100,000 square foot warehouse where these kits come in, they restock them and send them back out to you guys. And I said, what happens if your racks are nicely tied, but we have an earthquake now and their boxes slide out? This is in Memphis, very high seismicity. And he said, we'd be out of business. We got to go through and do QA, QC on all of that material, then resort it, everything. And I said, all you need is to put some restraints or lips right in the front here, attach it to the existing rack, and you're good to go. He said, really? I said, yeah. He said, oh man, University of Memphis, their mechanical engineering department, I can get them to make me some plastic angle strips that will bolt right to it. And I said, perfect, it'll work. Employees can still get the box out. So that's what he did. That's smart mitigation. Benefits of mitigation. Like I mentioned before, life safety risks reduced. If I can leave anything with you, it's do it right the first time, okay, from today going forward. Your long-term strategy, anything new that you do it addressing natural hazards. And then by the time the natural hazard comes along, you're going to be in a much better position to actually resist that. So any renovations, new equipment replacements, that's the time to do the mitigation. When you're replacing it, just put it back in new, rather than go and try to go through your entire thing. That's smart mitigation to me because we don't know when the natural hazard is going to occur and affect your facility. Some resources, FEMA 396, FEMA 577, jot that one down. Anything you see FEMA by is free. I love free. And these are actually very good documents. So FEMA 577 is actually very helpful for your design professionals that address all natural hazards. So jot that one down. That's available on their website. Final thoughts. Again, design professionals, it starts with them because they're in tune with this, but they often don't have the expertise for addressing natural hazards. A normal building, they do. Construction inspection, vitally important. Incorporate a housekeeping policy, particularly for earthquake mitigation. And make sure everything's properly anchored. This is where you want to end up, is very good performing facility after natural hazards, or you're able to provide that service to the community, right? This is just another video real quick that I have. Go ahead and roll it. This is just some clips from the Japan earthquake. And just to show you, you don't hear much in the way of seismic damage from shaking from that earthquake. There's a reason for that. Very good building codes, very good enforcement. It was the tsunami that did the high majority of the damage. But we saw the building in the shake table move, right? That's not unreal. This is actual footage. Again, we don't have warning. We don't have 12 minutes to evacuate to the interior. It's happening now. What are you going to do? That's a large section of ceiling coming down. Tokyo was well removed from the major epicenter region, so the shaking wasn't that great. Contents.
So this is in Tokyo?
This is in Tokyo. This is outside. This is why you don't want to run outside when it's shaking. Drop cover and hold on. Wait till shaking stops. When you look at some of these, it's funny. That rack fell over, the light's swinging, but look at the CPU and the monitor. It's still sitting there. Just like tornadoes, doesn't grab everything for whatever reason. Notice this large monitor behind this woman right here. You guys have a lot of monitors in your facilities. I would have thought the Japanese would have dropped cover and held on, but I haven't seen anybody do that. That's all I have. Any